We have seen in the previous video how to represent cascaded coupled transmission line bandpass filter to cascaded transmission line sections with admittance inverter J1, J2, J3 until Jn plus 1, where n plus 1 is a number of the cascaded coupled line transmission line sections. And we said that this configuration is much simpler to be used to design the bandpass filter, and the main target of the design is to determine the values of G1 until Gn plus 1 of the different inverters, and from these values we are going to determine Z even and Z odd, and from Z even and Z odd we can determine the dimensions of the coupled line transmission line sections. So in this video we are going to study how to design a bandpass filter based on these cascaded inverters. Effectively, this equivalent circuit is composed mainly of three parts. The first part is transmission line section of electrical length 2 theta, because we have here an electrical length theta connected to an electrical length theta. So this transmission line section is equivalent to a transmission line section of characteristic impedance Z node and electrical length 2 theta. In addition, we have inverter inside the circuit. In addition to the inverter inside the circuit, we have edge inverter. This edge inverter is connected to a transmission line section of phase shift equal theta only. So this is a special case because the inverter inside the circuit is connected to theta from this side and to theta from this side, and this theta or this electrical length theta is connected to a similar electrical length theta. So the transmission line inside the circuit itself is 2 theta, but at the edge of the circuit it is only 1 theta. So this edge at the beginning of the circuit and at the end of the circuit. So the beginning and the end of the circuit are special cases, but inside the circuit is composed of multiple sections of 2 theta transmission lines and inverters. For the case of the transmission line of electrical length 2 theta, its equivalent circuit, it can be represented as a T circuit with impedances minus JZ node cotan theta minus JZ node cotan theta, and shunt admittance JZ node over sine 2 theta, connected to a transformer from 1 to minus 1. This circuit can be simplified as a parallel LC circuit at the resonant frequency. The resonant frequency when theta equal pi over 4, so 2 theta equal pi over 2, or in other words, the length here, if theta equal pi over 2, so 2 theta it will be pi, so this length would correspond to lambda over 2 at the center frequency. So if the length is lambda over 2 at the center frequency, this open circuit transmission line section would be equivalent to a resonant parallel LC circuit, where the value of L in this case would be 2Z naught over pi omega naught, And the value of the equivalent capacitance in this case would be 1 over omega naught squared L. So it would be pi over 2z naught omega naught. And the resonant frequency, omega naught squared, would be 1 over LC. So the open circuit transmission line section of length lambda by 2 and characteristic impedance Z0 has an equivalent circuit of parallel LC circuit, parallel or resonant parallel LC circuit with this value of L and this value of C. So each section of 2 theta transmission line Z0 here can be replaced by this parallel LC circuit. Okay. Now for the case of the edge transformer, assuming that we are talking about J1 or Jn plus 1, J1 is connected to a transmission line section of length only theta. Theta is equivalent to pi over 2 or length lambda over 4. So pi over 2 or lambda over 4, it corresponds to a phase shift pi over 2, or means that we have J. In this case, the ABCD of the transformer connected to a transmission line section of length lambda by 4 can be obtained as the ABCD of the transformer multiplied by the ABCD of a transmission line of length lambda over 4. Assuming that the inverter has inverting value J, and by normalizing the inverter to Z0, which is the characteristic impedance of the filter, so the turns ratio of the filter, of the inverter, it would be N equals J multiplied by Z0. J here is the ratio of the inverter, the normalized inverter. So in terms of the characteristic impedance Z0, the ratio of the inverter N would be J multiplied by Z0. The ABCD of such inverter in this case would be 1 over N 0 0 N. On the other hand, the ABCD of lambda by 4 transmission line section is 0 minus J Z0 minus J over Z0 0. By multiplying the ABCD of the transformer by the ABCD of the transmission line section, we can obtain the ABCD of the transformer connected to transmission line section of lambda by 4. So the ABCD of this section is 0 minus J Z0 over N minus Jn over Z0 0. Okay. In a similar way, we can obtain the ABCD of the first inverter. Now we have the ABCD of the inverter itself. We have the ABCD of the transmission line section of 2 theta. We have the ABCD of the edge inverters. By cascading all the ABCD of these sections, we can obtain the ABCD of the complete filter. So, assuming that we have cascaded coupled line transmission line section of order n equal to, so the equivalent circuit based on cascaded transmission line section Z0 with inverters would be J1, J2, J3. Here we have 2 transmission line sections of 2 theta, which can be replaced by LC parallel, LC parallel, and effectively because this Z naught and this theta, effectively L1 equal L2 and C1 equal C2. But let us now call it L1 C1, L2 C2. Now, and the first inverter combined with the lambda by 4 transmission line section would be represented as a transformer with a transformer ratio Z node G1 to 1. In a similar way, the last inverter with a transmission line section of lambda by 4 will be replaced by a transformer 1 to Z node J3. And here we have the load Z node. The remaining part is the internal transformer. So the internal transformer is J2 with phase shift 90 degrees. Okay. So this is the equivalent circuit for a cascaded coupled line transmission line section of order 2. Now it is required to determine the input admittance at the input port. This can be obtained by the admittance of L1 C1 plus the transformed or in admittance through the inverter J2. The transformer admittance through the inverter J2, at the beginning we obtain the admittance Z node transformed through this transformer, then it is parallel to the admittance of L2 C2, then all this admittance is transformed through J2, and this would be parallel to the admittance L1 C1. All of this stuff will be transformed through the transformer 1 to GZ, 1 to Z node J1. Okay, and it should be noted here that 1 over L1 C1 equal omega naught squared, and also 1 over L2 C2 equal omega naught squared. So we can replace the ratio 1 over LC for L1 C1 or L2 C2 by omega squared. Okay, let us do this. The input admittance Y input would be 1 over the transformation ratio squared, 1 over G1 squared Z naught squared, multiplied by the input admittance here. The input admittance here would be the admittance of the capacitance J omega C1 plus the admittance of the shunt inductance would be 1 over J omega L1 plus the input admittance seen from the inverter J2. The input admittance from J2 would be J2 squared over the input admittance seen from here. The input admittance seen from here would be J omega C2 plus 1 over J omega L2, which can be arranged as square root or J square root C2 over L2 multiplied by omega over omega naught minus omega naught over omega plus the admittance seen from this transformer. The admittance seen from this transformer is Z naught Z naught squared J3 squared multiplied by 1 over Z naught. So it would be Z naught multiplied by J3 squared. Now by arranging this part as J square root C1 over L1 multiplied by omega over omega naught minus omega naught over omega. This is simply by multiplying by square root L1 over C1 multiplied by C1 over L1. So by multiplying this, we can obtain this relation directly, keeping in our mind that omega naught squared is 1 over LC. So this is the input admittance of this filter in this case, or this is the input impedance of this circuit. It is not filter right now. Alright? On the other hand, if we are talking about second order bandpass filter, for the second order bandpass filter, we are going to convert the series L by a series resonant circuit L2C2, and the shunt capacitor would be replaced by a parallel resonant circuit L1-C1-, and the values of L1-C1-, L2-C2- are determined by using the prototype of the low pass filter according to the value of G1 and G2 and according to the required specification of the low pass filter. In this case, the input admittance of the bandpass prototype would be obtained as J omega C1 dash plus 1 over J omega L1 dash, the input admittance of this part, plus the input admittance of this part, plus the input admittance of this arm. The input admittance of this arm is 1 over J omega L2 dash plus 1 over J omega C2 dash plus Z naught. So this is the input admittance for the bandpass prototype filter. By arranging this formula, we can arrange it as J square root C1 dash over L1 dash multiplied by omega over omega naught minus omega naught over omega plus 1 over J square root L2 dash C2 dash omega over omega naught minus omega naught plus omega plus Z naught. This actually is the input admittance from the prototype of the bandpass filter. Now, by equating the input admittance from the equivalent circuit of the cascade transmission lines with the inverters by the input admittance of the prototype of the bandpass filter, we can see that the input admittance of the equivalent circuit has the form of J something multiplied by omega over omega naught minus omega naught over omega, which correspond to another term here in the admittance of the prototype of the filter, plus another term here or something similar here. Okay, so by equating every corresponding term, we can say that the square root of C1 over L1 multiplied by 1 over J1 squared Z naught squared, this would equal the square root of C1 dash over L1 dash. Should be noted here, C1 and L1 are the equivalent LC circuit for a transmission line section of length pi over 2. Oh, sorry, pi over 2 or pi over 2. Yeah, pi over 2. Pi over 2 is lambda by 4. Pi. Sorry. Pi. So C1 and L1 are the equivalent LC circuit for a transmission line section of length lambda over 2. Lambda over 2 correspond to theta equal pi. Okay? Alright. But C1 dash and L1 dash are corresponding to the value of LC of the series resonant circuit of the prototype of the bandpass filter. So this corresponds for something and this corresponds for another something. Okay? Now by equating this term multiplied by this term with this term, which is multiplied by omega over omega naught minus omega naught over omega, we obtain that 1 over G1 squared Z naught squared multiplied by square root C1 over L1 equals square root of C1 dash over L1 dash. In a similar way, by equating this term with this term, so in this case, C the square root of C2 over L2 over J2 squared multiplied by J1 squared Z naught squared would equal square root L dash 2 over C2 dash. So once again, J1 squared Z naught squared over J2 squared multiplied by square root C2 over L2 equals square root of L2 dash over C2 dash. Finally, by equating the term without omega here, can be noted that Z naught multiplied by J3 squared multiplied by Z naught squared multiplied by J1 squared over J2 squared equals Z naught. Now by eliminating Z naught with Z naught, we can say that, or without eliminating, J1 squared Z naught cube J3 squared over J2 squared equal Z naught. What is the advantage of this? Actually, the advantage of these equations relate the values of the inverter J1, J2, and J3 and the values of the equivalent LC circuits for the transmission line sections between the inverters to the values of the LC circuits of the bandpass prototype filter. So when we are going to design a bandpass filter, we start from the prototype, and from the prototype we determine L1 dash, C1 dash, L2 dash, C2 dash according to the prototype and according to the required omega naught and the bandwidth and everything and Z naught. And from these values, we can now determine the values of J1, J2, C1, L1, C2, L2, and so on. Actually, we are interested in J1, J2, and J3. Yeah, J1, J2, and J3. The values of the inverters. And from the values of the inverters, we are going to determine the specifications of Z even and Z odd of the corresponding coupled transmission line sections. Hopefully, you are following me. Okay. So, as I said, from the prototype of the low-pass filter, we obtain G1 and G2 because we are talking about second order. And from G1 and G2, we obtain the corresponding L1 dash, C1 dash, L2 dash, C2 dash, according to the required center frequency, the required bandwidth, and the required characteristic impedance. Now, according to the relations which we have obtained right now between the values of the inverters and the values of C1 dash, L1 dash, C2 dash, L2 dash, we can obtain the values of the inverter. So the values of the inverters by using these two relations can be obtained as J1 Z0, this one, would be C1 L1 dash over L1 C1 dash to the power 1 over 4 from this equation. And effectively, C1 dash is given by G1 over delta omega naught Z naught. This is C1 dash. L1 dash is delta Z naught over omega G1. So by dividing L1 dash over C1 dash, this can be delta squared over G1 squared over omega naught squared. Okay, L1 delta L over C, L1 dash over C1 dash would be delta squared Z naught squared over G, delta squared Z naught squared over G, and omega naught we eliminated this omega naught. Right? Okay. On the other hand, C1 over L1, C1 over L1, which are L and C, which are obtained from the equivalent circuit of the transmission line section of phase 2 theta. The value of L is obtained as 2Z naught over pi omega naught, and C, it was 1 over omega naught squared L, so it was by 2Z naught omega naught. So in this case, the value of L over C, assuming L1 over C1 or L2 over C2, it would be 2Z naught over pi. Remember that these values L and C are obtained from the equivalent transmission line section of theta equal pi. This one, when Z naught and we have 2 theta, we have equivalent L 2Z naught over pi omega naught, and equivalent C pi over 2Z naught omega L. Okay? Let us go back. Yes, we are here. So in this case, L dash over C dash is equivalent to delta Z naught over G. Assuming that we are talking about L1 over C1 dash, so this would be delta Z naught over G1. And L over C, assuming L1 over C1 or L2 over C2, it would be 2Z naught over pi. So means that C over L square root would be pi over 2Z naught. So in this case, we have y, we have 2, we have delta, we have G1. So this value to the power 1 over 4 is equivalent to the square root of pi delta over 2G1. Delta here is the bandwidth of the required filter. G1 is the value of G1 obtained from the low-pass prototype. Okay? Now, this was the first equation. The second equation, we have already obtained G1Z0 as this value. So, we can obtain J2Z0 is equivalent to J1Z0 squared multiplied by C2 dash over L2 dash. How comes? We are going to move J0 squared here, J2 squared here, and this is C2 dash, L2 dash, and we have G1Z0 squared. So by multiplying this side by Z0 squared, this would be G1Z0 to the power 4. So by taking the square root, it would be J0Z0 would be G1Z0 squared multiplied by C2 dash, L2 dash to the power 1 over 4. And already we have G1Z0 equal square root by delta over 2G1. So this can be replaced by Z0 multiplied by this square root. And then the remaining part, C2 over L2, will be replaced by pi over 2Z0. And C2 dash over L2 dash would be replaced by G over delta Z0. And because here we are talking about 2, so this would be G2. Okay? Now by integrating all these parts together, we find that G2Z0 equal pi delta over 2 square root G1 G2. Right? Finally, we have J3 Z0 can be obtained as we will take J3 squared Z0 squared. The remaining Z will be eliminated by this, would be J2 over J1. So by taking the square root, we can obtain J3 Z0 equals J2 over J1. J2 over J1, by dividing this by this, we can find out that J3 Z0 equals the square root of pi delta over 2G0. Now, we could obtain the value of the three inverters, G1, G2, G3, in terms of the prototype of the low-pass filter, G1 and G2, and the required bandwidth delta. By using these equations, we can obtain the values of the inverters, and for each inverter, we can determine the even and odd impedance of the coupled line transmission line section. So for each inverter, the corresponding coupled line transmission line section will have Z0 even equal Z0 multiplied by 1 plus J Z0 plus J Z0 squared, and Z odd would be Z0 multiplied by 1 minus J Z0 plus J Z0 squared. This will be applied for G1, G2, G3. And each time we have even impedance and odd impedance. From the even impedance and odd impedance, according to the value of of odd impedance and even impedance, we find the intersection point, and from the intersection point, we find the value of the spacing S and the value of the width W. So for each inverter, we are going to determine the value of W and S, which they have the inversion ratio of such inverter. Now, by cascading such coupled transmission line section, we obtain the performance of the required filter according to these inverters. Okay, I hope that is understandable. Now, this analysis is actually based on n equal to or 3 cascaded coupled transmission line section. What will be the situation if we are talking about n greater than 2? For example, 3 or 4 or 5. In this case, the values of the inverter for the first inverter would be the square root of pi delta 2G1. Effectively, this is the same as the previous one, pi delta over 2G1. And the inner inverters would have Z node Jn, where n is 2, 3, 4, and so on, equal pi delta over 2 square root Jn minus 1 multiplied by Jn. For the previous case where n was only 2, it was J2 equal pi delta over 2 square root J1 multiplied by J2, which was this one. So this in general case for any cascaded coupled transmission line section, it is Z node Jn is pi delta over 2 square root Jn minus 1 multiplied by Jn. The final or the last inverter, Jn plus 1, would be the square root of pi delta over 2 Jn plus 1. Effectively, this was, in this case, pi delta over 2J2 multiplied by J3, and J3 in this case was 1. So in this case, it was pi delta over 2J2J3. Here, for n plus 1, would be pi delta over 2Gn plus 1. And once again, according to the values of the transformer 1, 2, 3 until n plus 1, we are going to determine Z even and Z odd. And for each transformer, we are going to determine the width and the spacing of the corresponding transmission line section. It should be noted that the lengths of the coupled transmission line sections are fixed to be theta equal pi over 2 at the center of the bandpass. So at the center of the bandpass, the lengths of the coupled line transmission line section are lambda by 4. So all of the transmission line sections have the same length, lambda by 4, but the width and the separation between the coupled line transmission line section will be different from one section to another section according to the corresponding inverter value. This is how to design a bandpass filter by using coupled transmission line sections. In the following video, we are going to see an example about this. Okay?